I'm presenting our paper titled Industry 4.0 Driven Statistical Analysis of Investment Casting Process Demonstrates the Value of Digitalization. It is authored by myself, Rose Clancy, Ken Bruton, Dominic O'Sullivan, and Dermot Keogh. This research was part funded by Science Foundation Ireland through the MARI SFI Research Centre for Energy, Climate and Marine, with supported funding obtained from Dupuy Centres. The purpose of this study was to perform statistical analysis of manually collected data in an area of the manufacturing organization that is not digitalized, in order to show the value that can be achieved through digitalization. The insights gained through analysis of the data can be used to drive decision-making in relation to the optimization of input parameters and minimize the quantity of defective parts. A number of scientific questions were set to establish the relationship between the quantity of scrap products and the level of silica component in the ceramic slurry. A series of independent t-tests were conducted to address these questions, and the results from these t-tests showed the optimal level of silica in the binder of the ceramic slurry to minimize the rate of a particular scrap type caused by thin or weak areas of the shell. The German initiative Industry 4.0 is a strategic approach to the digitalization of manufacturing. Factory digitalization refers to the digitization, integration, and automation of data flows in production through, for example, the use of digital sensors and Internet of Things technology. While Industry 4.0 can be described as a vision of how manufacturing will be done in the future, factory digitalization is seen as a key enabler of getting there. By creating a connected environment through digitalization, businesses can extract and use key information from their processes in real time to inform decision-making, resulting in improved supply chain management and performance. However, one of the biggest challenges is presenting a defendable business case to management to justify the significant cost associated with digitalization of the supply chain. Therefore, the objective of this research is to employ statistical analysis to identify if relationships exist between process variables using historical, manually collected, non-digital data, and to use insights gained from this analysis as leverage for justifying the implementation of a digital data acquisition system. The research is carried out with an organization that is one of the largest manufacturers of orthopedic implants. The focus of this work is a value stream in the organization known as a foundry, which employs investment casting methods. The investment casting process is as follows. Firstly, the wax beads are melted and injected into a pattern mold. Then the wax pattern is dipped into a ceramic slurry, usually 4 to 6 times to form the ceramic shell. It is also dipped into a coarse refractory stucco and dried in between dips. It is then placed in an autoclave to melt and remove the wax from inside the ceramic shell. The ceramic shell is then filled with molten metal that solidifies, and finally the ceramic shell is removed mechanically to obtain the metal part inside. The production of the ceramic shell is a critical part of the investment casting process. It is a labor-intensive, time-consuming process, and it is difficult to avoid occurrences of defects in the investment casting process. In some studies, investment casting has reduced failure rates of up to 40%. These defects are often caused by non-optimal settings of process parameters, and research agrees that data analysis of historical data is required to identify the optimal range of parameter settings, and hence reduce the quantity of defective parts in an investment casting facility. Research in this area also stated that it is becoming imperative that the investment casting industry improves current casting quality and reduces manufacturing costs, and that the optimization of the mechanical and physical properties of the ceramic shell will be fundamental to achieving these aims. Therefore, I conducted statistical analysis to test if a relationship exists between the quantity of scrap defects and the level of silica, which makes up the main part of the mold. Research states that the ingredients in the ceramic slurry play a crucial role in the properties of the shell. However, there have not been studies with statistical analysis to determine if the level of silica in the binder is related to the strength of the shell and the failure rates caused by poor shell strength. So a change is made to the silica level in this prime slurry. So it was reduced by 8% to test if there is a difference in the average level of the 3 most common scrap types. The SiO2 level is the percentage silica of the binder solids in the slurry mixture for the slurry. Level 1 had a higher level of silica in the binder, and level 2 had a lower level of silica in the binder. The labels X and Y are used to represent the actual numerical values of the silica levels during this time period, as it is sensitive information to the organization. However, I can say that the organisation operates within a tighter limit of the typical industry range, 22% to 32% silica. The goal of the statistical analysis in this project was to investigate if reducing the level of silica would result in a statistically significant difference in the quantity of scrap. The three most common scrap types for the foundry manufacturing process were selected for analysis. As this scrap information is sensitive to the organisation, they will be referred to as scrap type 1, scrap type 2, and scrap type 3. 3 scientific questions were set. The first was to test if there is a difference in the mean quantity of scrap type 1 at the upper and lower level of silica. The second was to test if there is a difference in the mean quantity of scrap type 2 at the upper and lower level of silica. And the third was to test if there is a difference in the mean quantity of scrap type 3 at the upper and lower level of silica. SPSS was used to perform descriptive analysis and the statistical significant tests. A significant test is used to test a theory or hypothesis, and it involves 2 hypotheses. Firstly, the null hypothesis, which is assumed to be true, and it involves the hypothesis of no difference. Secondly, the alternative hypothesis, which contains all values that would lead you to reject the null hypothesis. The alternative hypothesis may be directional, one-tailed, or non-directional, which is two-tailed. A two-tailed test only asserts that the population parameters is different from the one hypothesis, whereas a one-tailed test states which direction the population parameter differs from that specified under the null hypothesis. The output from the statistical software provides a p-value which is used to determine if the null hypothesis should be rejected. If the p-value is small, i.e. less than 0.05, then we have a significant result and we can reject the null hypothesis. If we reject the null hypothesis, the researcher has provided evidence against the null hypothesis in favor of the alternative hypothesis. An independent samples t-test is an appropriate test to use for this study, as it is used to estimate whether the mean value of an outcome variable is significantly different between 2 groups of experimental units. It is typically used when the outcome variable is continuous and the explanatory variable is binary, which in this case is either the lower or higher level of silica. An independent t-test was used to test the first question: is there a difference between the mean quantity of scrap type 1 at the higher and lower level of silica? When conducting an independent samples t-test, the general rule of thumb is that if the standard deviation of one group is more than twice the other, then the results where equal variances are not assumed should be used. In this case, it is, so results where equal variances are not assumed is used. The results from the independent t-tests indicate that the null hypothesis can be rejected, since the p-value is less than 0.05. This leads to the conclusion that there is a statistically significant difference in the mean quantity of scrap type 1 between the higher and lower levels of silica. You can see that the mean quantity of scrap at the higher level of silica is 0.12 units per batch of products, whereas the lower level of silica is 0.03 units per batch of products. Therefore, a lower level of silica is suggested to reduce the quantity of scrap type 1. An independent t-test was also used to test if there is a difference between the mean quantity of scrap type 2 at the higher and lower level of silica. And in this case, the standard deviation of 1 is not more than twice the other, so the results where equal variances are assumed is used. The results from the independent t-test indicate that the null hypothesis cannot be rejected, since the p-value is greater than 0.05. This leads to the conclusion that there is not a statistically significant difference in the mean quantity of scrap type 2 per batch between the higher and lower level of silica. You can see that the mean quantity of scrap type 2 per batch is the same at the higher and lower level of silica. An independent t-test was used to test the third question: if there is a difference in the mean quantity of scrap type 3 at the higher and lower level of silica. In this case, the standard deviation of 1 is not more than twice the other, so the results where equal variances are assumed is used. The results from the independent t-test indicate that the null hypothesis cannot be rejected, since the p-value is greater than 0.05. This leads to the conclusion that there is not a statistically significant difference in the mean quantity of scrap type 3 per batch at the higher and lower level of silica. You can see this in that the mean is almost the same for scrap type 3 at the higher and lower level of silica. So the results from the t-test for question 1 reveal that there is a statistically significant difference in the average level of scrap type 1 at the higher and lower level of silica. This insight led to the development of a fourth question, because when looking at the data for the time period, it was noticed that the majority of scrap type 1 that occurred was for a specific product family A. is referred to as product family A, as this information is sensitive to the organization. Therefore, a fourth question was developed to test if there is a difference between the mean quantity of scrap type 1 for product family A at the higher and lower level of silica. An independent t-test was used to test this. The results from the independent t-test for the equal variances not assumed, as the standard deviation of 1 is more than twice the other, indicated that the null hypothesis can be rejected as the p-value is less than 0.05. This leads to the conclusion that there is a statistically significant difference in the mean quantity of scrap type 1 for product family A between the higher and lower level of silica. You can see that the mean quantity of scrap type 1 for product family A at the higher level of silica was 0.42 units, whereas at the lower level of silica was 0.13 units. This is quite a significant difference. In summary, the results from the first independent t-test indicated that there is a statistically significant difference in the mean quantity of scrap type 1 between the upper and lower level of silica. However, the results for the second and the third question indicated that there is not a statistically significant difference in the mean quantity of scrap type 2 or scrap type 3 between the upper and lower level of silica. The fourth question was developed as a result of finding that a relationship existed between the mean quantity of scrap type 1 and the level of silica in the binder. The results from the fourth question show that there is also a statistically significant difference in the mean quantity of scrap type 1 for product family A between the upper and lower level of silica. To recap, a statistically significant relationship was found between the level of scrap type 1 and the level of silica in the binder of the ceramic slurry. In other words, the statistical analysis showed that there was less occurrences of scrap type 1, in particular for product family A, when the silica level was reduced. Specifically, there was a 27.5% reduction in the scrap type 1 when the silica level was reduced. An example of scrap type 1 is shown in the figure. This type of defect is caused by thin or weak areas of the shell failing during casting, which allows metal to leak into the void of the shell. It is a very expensive type of scrap, as the molten metal has been poured into the shell at this stage, and the metal material is far more expensive than in comparison to the wax material. A defective product occurring at the metal stage could cost an organization $100 in comparison to a defective product occurring at the wax stage, which may only cost pennies. This analysis and identification of optimal parameter setting has resulted in a very large cost saving for the organization through the prevention of defective products caused by scrap type 1. In order to ensure that this reduction in defective parts is maintained, the silica parameter needs to be continuously monitored. To achieve this continuous monitoring, a digital data acquisition system was required. The slurry parameter levels, including silica, were previously recorded on paper, and a new system has since been implemented in which the information is entered into a wireless tablet. This information is then fed to a server that allows it to be brought into a business analytics platform for continuous monitoring. The study provides an example of how analysis of historically collected data can provide insights into relationships and improve the yield of manufacturing processes. Statistical analysis is a relatively easy method for practitioners to implement, and it is an approachable initial step that can be taken by organizations to begin and justify the value of the adoption of digital technologies in production. Thank you for listening, and please feel free to contact me if you have any questions.